Okay, final question then, number 9. So we've got to draw the shape of a molecule of krypton difluoride, including in our answer any lone pairs of electrons that influence the shape, name the shape, and then suggest a bond angle. So we've got KRF2. Now, looking at KRF2 then, we know that the F contributes, well, each F has 7 electrons in its outside shell and the KR has 8 electrons. So, thinking about how these two interact then, we're going to end up with 2 bonding pairs of electrons. So if I was to draw this, I would have KR with an F. KR with an F, we're going to have 2 bonding pairs of electrons and then 3 lone pairs on the krypton. Now, the only way for these lone pairs to be as far away from each other as possible is for them to sit around the krypton atom. Okay? Now, this molecule is quite difficult to explain because it's going to be 3D. Okay, so our F's are going to be linear and our lone pairs are going to be all around that krypton centre. Okay, so it's going to be linear with a bond angle of 180 degrees. Now, just to help you think about what this might look like then, if we were to draw this in 3D, it will be more like this. And then one more coming out underneath. Okay, so we've essentially got 5 lots of electrons around the molecule, but 3 of them are going to be as far away from each other as possible, so these are going to be our lone pairs. It's hard to draw. And then our F will be underneath and on top. Then there are 2 lone pairs of electrons on the oxygen atom in a molecule of oxygen difluoride. So we've got 2 lone pairs. We have to explain how the lone pairs on the oxygen atom influence the bond angle. Okay, so we've got 2 lone pairs of oxygen on the oxygen atom and 2 F's. So our lone pairs are going to repel each other, forcing the F's to be closer together. So we're going to make sure we mention the 2 lone pairs repel the bonding pairs. And so we're going to have an angle of around 103 to 106 degrees. And then finally then, we've got silicon tetrafluoride, which is a tetrahedral molecule. We have to deduce the type of intermolecular force, explain how these forces arise, and excuse me, and why no other type of intermolecular force exists in Si4. Well, I'm thinking immediately of my 3 intermolecular forces that I know. So I've got van der Waals, I've got dipoles, and I've got H bonds. Now, immediately I can see in this case there's going to be no H bonds. So I'm going to record that underneath. No H bonds as no hydrogen on the F. So we can get rid of those. Sorry, that's crossed out. We're not going to have any dipoles either. No permanent dipole. Permanent dipole. The reason for that then is the molecule is symmetrical. Leaving us to just have van der Waals forces. Okay, and the reason we have the van der Waals forces is because we've got 1 molecule of silicon tetrafluoride will induce a dipole in any neighbouring molecules. So this molecule